Hi, in this tutorial we will continue with our study of functional dependencies. Now we will um, check on the ways that we identify functional dependencies. So there are basically four ways. One is the trivial functional dependencies. Trivial functional dependencies is like the case of an attribute functionally determine itself or a set of attributes which functionally determine a subset of itself. So that's what we call that as a trivial case because that's always true. Um, and then the one that is really dependent on the type of database application that you have is the assertions. So for example, here, let's suppose that employees hired at the same year, meaning the years of experience will imply the same salary. So this is not always the case. That depends on the company. But for example, it does something that is true for the company. That's what we call an assertion. And then in this case, years of experience will determine salary. So that's one that is the one that is common. Now, the other possibility is the semantics. So for example, if we have a table that have address, zip, street, and zip code, so it is possible then with the semantics, I mean, it's something that is not an assertion. The zip code determines the city. And now the one that kind of complicates says, well, we can inspect the semantics and we could find the assertions or the constraints that are over the data. But then there are others that are kind of implicit. For example, here it says let R A B C. So it says the name of the table is R and the attributes are A, B, and C. And F is a set of functional dependencies over R. And then we can see that A functional determines B and B functional determines C. Then by transitivity, we could say that A determines C. But what we see here is that that wasn't really known. It wasn't explicit. It was something that we can derive. And in that case, we say that from the set F that contains two functional dependencies logically implies a third one, which is A determines C. And the notation is given by that. So now we have a question that says, well, maybe uh, there are functional dependencies that I don't see. How do I know that I'm done with the functional dependencies? Why this is important? Well, because we're going to use functional dependencies to establish the current normal form of a table, and in a table it's a good table. It's based on functional dependencies, so I need to actually know all the functional dependencies that apply for a table, for a given table. Then the way that I know that I don't have any other functional dependencies is by computing F plus. Going back to my previous example here, where I have a set F, this set F is some, this denotes that these are some functional dependencies over this table. Now, are they all? Well, in this case, they were not all because there was another one here. Now, what about the trivial? The trivial will be A determines A, B determines B, AB determines B. Remember that subset of determined itself. So then, to have a set that contains all possible functional dependencies is the one that we're going to call F plus. And that's what we're going to call the closure of the set. So that's the big F. So for example, for this example, the one that we were talking about, so we know these two, we knew this, and this is the case of the trivial, right? This is BC, and so on. So we got more for them to compute. So now, how is that we will compute all the other ones? Well, that's what we had the Armstrong's axioms, that we got those three rules: reflexivity, augmentation, and transitivity. And with those, we can use them to derive, I mean, once we know a set of functional dependencies, to derive the other, to compute F plus. Now, something else that they said about this theorem is that this is the sound incomplete. Sound meaning there will be nothing wrong, they will not derive anything incorrect. And complete, that means we don't need anything else. That's it. So those theorems are sound incomplete. However, um, we add in three more that they are not really needed there, but they are very useful. So the theorem says the first three are the ones that we need. We don't really need these two. So what we will do now as an exercise, we will prove that these are not needed using the other three. So let's start with rule number 4, the decomposition. So again, what we say is this is a set. This symbol, the line with the equal sign, says this set, this rule. I mean, if we know this is what we know, this is what is given, then we can logically imply this. So if we know that x derives implies y and z, we can say that x implies y and x implies z. So the way that we do it is we have statements and we make a reference of how we have the statements until we prove it. So my first statement will be what is given. So I have my first statement is the following. And then I justify here and I say this is given. Now again, I want to derive some statements here that are true until I find this. This is what I want. Now, by using rule 2, I also know this. If I have this, one of the trivials is this. And then we say here by rule 1. Then my third statement, I can also say this. This is also true, right? By R1. Why? Because Z is a subset of this side. Y is a subset, so this is true. I'm not proving this, this is given. This is what they say. If this equals from this is it. Okay, now we can do transitivity. Look, x implies yz and yz implies y. So transitivity is rule 3. So my fourth statement will say by transitivity I can say x implies y. How? By using statement 1 and statement 2 on R3. So here is the justification of the validity of why this is true. So this is my fourth statement. Then we put a check that says this is what we're looking for. So I got one of my the things that we were wanted to prove. Now I can apply the transitivity on 1 and 3 too, because y implies yz and yz implies z. Then that will be my fifth statement. Then x also implies c. How? Well, by using 1 and 3 on with 3, right? And then this is my other statement. So we're done with the R4. Now let's do the same with R5. So the R5 is the union rule. So for the union rule, we have this. So what we're illustrating is what we said in the theorem that we only need the first three uh, rules from Armstrong, the first three axioms. Is what it means that it's complete. We don't need anything else. But we said, oh, we're adding three more that are very useful. Union. Okay, so let's do the same. So the proof is we have a statement, so we go with the given. So we got given what? X and Y. So we're labeling that as my statement number 1. And then number 2, we have X implies Z. That's also given. So this is given and this is given. Now we want to go here. So then we can also say that xz So if I z in those two sides, that will be documentation rule. That will be the same as doing yz. So this is by rule 2 on 1, right? So I'm adding the z in those two sides. And then I can do the same with uh, so I can do xy, and then yz. So I'm doing rule 2 on 2. Then as my fifth statement, I can add also x, these two sides, x, x, xy. Now, because this is a set, x is the same as just x implies xy. And then this is by rule 2 on 1. Oops, sorry. And then my sixth statement, I can do some transitivity because I know that x is xy and xy I know is yz. So then we can say that x implies yc, and this is by transitivity on 5 and 4. And this is what we wanted to prove. Now we will solve an additional exercise in the next tutorial using this. I mean, I just checked, I mean, did R4 and R4 and R5, but that's the same on X6 and X6 that you can see in the tutorial, in the PowerPoint, I'm sorry. Okay, thank you.